Šukilović. She will talk about invariant geometries of the cotangent bundle of the Heisenberg group.
Thank you. Thank you very much. Thanks to the organizers for inviting me. As a previous speaker, I'm also coming from the geometry background, so it's not going to be completely theory of representation. But what I want to show you today is something that our group Invariant at the University of Belgrade is working on, and to just give you some ideas. I'll try to make it as simple as possible, not to go into too many details. So first, I will speak about cotangent bundle of Heisenberg group, because it's something that, well, it's not that surprising, but it's less commonly used, that a cotangent bundle of the Heisenberg group with appropriate multiplication. So the definition of a multiplication can be a Lie group itself and have all the nice features of Lie groups. And then I will talk about Riemannian and pseudo-Riemannian structures on this space. And in the end, I will say something about sub-Riemannian structures, because sub-Riemannian geometry is something that I'm primarily interested in these days. So our goal was to classify all left invariant metrics on Lie groups and understand their geometry. And we did not want to just focus on Riemannian or positive definite signature, but on all signatures. And this was the first thing that we were doing, because we want to give an answer to a much broader question. It was a question of geodesic or projective equivalence of metrics. In the meantime, we proved that statement in a completely different way by the classification problem. And then we just trying to give an answer to this question. We found that a lot of people were doing in this realm, and that the classification of metrics on Lie groups is very, very much, let's say, investigated field. In the Riemannian case, everything starts with a famous Milnor paper from '76, and then why is this paper so famous? Because it has geometrically beautiful construction. So he's just looking at the cross products and using cross products and geometric tools to complete classification of Riemannian metrics on Lie groups in 3 dimensions. And then it's their curvature properties in some very nice and invariant way. And then there are the people that are mainly doing the nilpotent Lie groups and nilpotent theory. They're all famous, were well acquainted with the works of Kaplan from '85. He was looking at the Heisenberg type groups, but this comes from the theory of hyperelliptic operators and partial differential equations. So it's not the language that are most of us very familiar. And then there are famous series of paper by Patrick Eberlein for the '90s, and he's focusing on two-step nilpotent Lie groups in completely geometric language. So this is something that we all start with. Pseudo-Riemannian case, interestingly, is not that, okay, these are all old results, but in pseudo-Riemannian case, it came much later. So it comes from '92 first results. So on the Heisenberg group H3, Lorentz metrics were classified. And then in '94, it was shown that all left invariant metrics on two-step nilpotent Lie groups are complete. And there was even an example of nilpotent Lie group in dimension 4 that is not complete. So it was really interesting to see that there, okay, it's not two-step, it's three-step nilpotent Lie still. And sub-Riemannian case is mostly investigated from the viewpoint of Heisenberg group, and it's very, very well understood. But as I will say in the end of this talk, there are some still open questions. So there are sub-Riemannian geometry is fairly new, let's say, topic in geometry. It comes mainly from the theory of optimal control, and people working in this area are usually coming from the theory of optimal control. It starts from the '80s. And then there are various authors starting from the 2000s up to now. There are a lot of topics on the sub-Riemannian geometry. So the partial results, because I'm first going to talk about classification, comes from the '80s and the famous Berger's paper. And then all the metrics of Riemannian signature in dimension 4 were classified. And for the nilpotent Lie groups, there are many results for Riemannian signature in dimension 3 and 4. Jorge Lauret investigated nil manifolds, and then our group just did the 4-dimensional case for both Lorentz and neutral signature. And in 5 dimension, there is a result by Kumola and Kowalski for dimension 5. There is also a series of papers by Kondo and Tamaru in early 2020s. They're just looking at the Lorentz signature of matrix on a special case of nilpotent Lie group. And one more is actually for arbitrary dimension. There was a proof that actually the classification of all Riemannian and Lorentz signature metrics on Heisenberg group of arbitrary dimension. The Riemannian case was in some way already known, but Lorentz case was completely new. And in the sub-Riemannian case, there's a couple of papers by Biggs and Nagy there, where they just did a classification of sub-Riemannian structure. So this is all in nilpotent. In solvable, we did, so this is all our group, we did mainly, all solvable groups in dimension 4, and then special cases of real and hyperbolic space, both in Riemannian and pseudo-Riemannian signature. And after this, I hope that this will be the end. I will not do classification anymore. It was enough, but then came COVID, and after that there was a huge conference and a lot of people came, and they started asking some questions, and then we wanted to find example and then give them answers, and then that led to the topic that I'm going to talk about today, because we wanted to find the answers, and then that it was like back to the drawing board, and then we started to. Okay, we were ambitious. We wanted to just, find one group and all the examples will be there. Of course, it was not true, but we were aware of that. So today's talks is actually based on 3 papers done by our group. The first one was published last, but it was written first, and it's only for a special dimension. So the title's a little bit misleading. But this is cotangent bundle of standard Heisenberg 3-dimensional group, so it's 6-dimensional example. But the other 2 are for arbitrary dimension. Okay, so let's talk a little bit about the cotangent bundle of Heisenberg group. So we start with the standard things. We start with the Lie group. It's manifold. That is also a group because we have multiplication law. Then we have Lie algebra, which is the tangent space in the identity element. And then throughout this talk, I will always assume that vector fields are equivalent to the derivations on the group. So for me, it will be the same objects. And then I can also simplify things, because it's not always easy to talk about the group and the metric on the group. But because we are working on a Lie group theory, then there is a unique way to extend the inner product on the Lie algebra to the left invariant metric on the Lie group. So instead of looking at metrics and groups, we are looking at inner products and Lie algebras. It simplifies the talk very much. So how can we construct the cotangent Lie group? So we start with the Lie group, we start with the cotangent bundle, and then we identify the 0 section of the cotangent bundle with the Lie group itself. And the fiber over the identity element, we identify with the dual algebra of the initial Lie algebra. And then as a Lie group, the cotangent bundle is the semi-direct product of the initial Lie group and the dual Lie algebra. And that semi-direct product is defined by the coadjoint representation. So it's mainly standard, but the people working in Lie groups are not using this that much. So it was interesting. And then, as expected, the corresponding Lie algebra is also semi-direct product of the initial Lie algebra with the dual Lie algebra using the same semi-direct. So the Lie algebra of the Heisenberg group and dimensional just is defined in the following way. What is actually important, we have 2-dimensional part and then 1-dimensional part. That 1-dimensional part is the center of the Lie algebra, so it's one element that commutes with all the others with respect to the Lie bracket. And then, of course, the dual algebra is going to be abelian, but I will also just put it in two parts, and I will explain why. So it's going to be this dual of this dual of this one. And then I can define conjoint representation in a standard way. Here, there can be minus, there doesn't need to be minus, just it depends what do you want to use as a standard. So we'll see here. So if I have all of these, then I can just define the Lie bracket on this new algebra, and I define it in the following way. So what I expect on the algebra level, I must have Lie bracket. And on the dual algebra, I have something that is defined using conjoint representation. And now I will just use it while I'm still here, just to perturb our basis a little bit. Why? Because it's somehow easier. So see, this is dual of this one, and this was the center of the Heisenberg algebra. Why I'm doing this? Because this part here will be the center of new Lie algebra. So it's much easier, and the formulas will be much nicer and easier to follow. So I'll just use this perturbation of the basis. And then I have left invariant vector fields on this new Lie group, and it's not surprise at all. So what I have complete lifts of left invariant vector fields in the initial Lie group, and then I have vertical lifts of Naur-Cartan left invariant forms on the initial group. So it's something that we definitely expected, and this is basis of left invariant vector fields that will span our Lie group. And when you read the standard results, they usually, when working with this group, they're usually working with a standard metric, because naturally you can define ad invariant metric. But that ad invariant metric, as you see, it's very naturally defined. But the thing is that this is neutral signature, and this is not something that people like to work with. But it has some nice properties that both Lie algebra and its dual are totally isotropic, meaning they coincide with their orthogonal complement with respect to this metric. Interestingly, this ad invariant metric is unique, and it's flat, meaning flat by standard meaning of the curvature. And this is something that we proved in the dimension 6, but then we discovered there is a proof for the, okay, maybe simultaneously, but it was earlier in the archive. So the result by Conti, Del Barco, and Rossi that this ad invariant metric is unique for every dimension. And then let's talk a little bit about structure on this group. So now we know the space, so let's see how can we measure it. So when we're doing that, as I explained, we are going to talk about actually classification of metric algebras. So I have Lie algebra, and I have inner product on it. And then I have Riemannian, when I say here Riemannian, also pseudo-Riemannian space of Lie group with a metric. And there is a proof, there is a theorem by Alexievsky that two metric Lie algebras, so algebra with the inner product, are isometric if and only if their corresponding Riemannian spaces are isometric. And there is also a theorem that says that if Lie algebras are completely solvable, meaning that their ad operator has only real eigenvalues, then isometric means isomorphic. Usually it's not always true, so only for completely solvable algebras. But there is a wonderful algorithm given by Gordon and Wilson in '88 that will give you an algorithm to check if two solved manifolds are isometric. Interestingly enough, in the dimension 4, all solvable actually are, let's say, this algorithm gives the trivial solution, so this holds for all solvable. We don't need completely solvable, but it's just because it's dimension 4. Okay, so what is the idea behind the classification? So we want to classify metric algebras. Well, here we have only one algebra, which is okay. So we are classifying inner products, and there are two approaches. in the literature. First approach is to fix the basis of the algebra such that the corresponding metric will have the simplest form. Meaning, if you want to classify Riemannian metrics, you just have identity metric, and then find structural constants. This is not bad approach, but the problem is you have a lot of structural equations, and then you additionally have to check if some of the corresponding algebras are isometric. And this is okay if you want to have some subgroup. For example, you want to classify all Riemannian Einstein metrics or Ricci flat or Ricci parallel. And this approach was done for Lorentz signature metrics in 4-dimensional. I think it's a paper by Calvaruso, and it's great. But the problem is there are no partial results. So you either complete the classification or you don't. And we don't like that. So we use the second approach. And the second approach is to fix the basis of Lie algebra such that structural equations are given actually by the classification. You know that the classification of Lie algebras is also, in general, open problem, but nilpotent and solvable Lie algebras are all classified up to dimension 6. So we know, so this is it. And then what are we going to do? We are going to look the simplest form of, because our inner product will be represented by a symmetric matrix, and then we'll act on that space of symmetric matrices by the group of automorphisms of Lie algebra. Why? Because it preserves Lie bracket, so we will not change the structural constants. So the classification is actually finding symmetric matrices, again, of arbitrary signature modulo the action of the automorphism group. Okay, and then here's first lemma that said, okay, let's look what the automorphisms of our Lie algebra look like. And then just remember, so we actually have 3. So these are block matrices. F1, F4 are correlated. So F1 has a part that is almost symplectic matrix. And then these others, so these are vectors, this is number, they're correlated to define this F4. F3 is completely arbitrary matrix. It doesn't have to be even invertible. So it's completely arbitrary. And then this is the action that we have. What do we know? Well, we know how many parameters by this action we can expect. Yeah, so we have the dimension of the space of all matrices. Then we have the dimension of automorphism group. And then I know that when I do this, I will have it at the most n times 12 plus 1 parameters. And then let's see how it looks like in Riemannian case. So in Riemannian case, we actually have this block matrix. So this one, okay, is diagonal matrix. And these sigmas, they are determined, actually, they come from Heisenberg. We can just make them so the last one we can set to be 1. All the other can be just ordered. They can be ordered, so just going down. And then the other part, this one, it comes also from Heisenberg. It's just because this is Riemannian, it's just larger than 0. And then we have this central part. This corresponds to the cotangent part of the group. And then we have this matrix S4. We have 0 somewhere, but generally we cannot simplify it. So let's see why. So the first was, okay, we have some matrix, we have a lot of parameters. Okay, we expected that. But can we do a little more simplification? Because we have this, which is diagonal. Can we diagonalize this matrix S4 as well? The answer is unfortunately no. Why? Well, because I want to preserve this one. So if I want to preserve the diagonal matrix, then only I can just do the symplectic rotations. And this is very narrow thing that we can do. So in general, the answer is no. But if we have some equals, then this class is much wider and we can further simplify this. But this is from case to case. So in general, this is how all the Riemannian inner products look like. Okay, and then I will talk a little bit about pseudo-Riemannian. In arbitrary dimension, this is impossible to do. And I will show you why, because even here, for the most basic example where we have the Heisenberg group H3, we will have 19 families of inner products. That's too much. So if I can get H5, then we'll just grow up exponentially. But here is the idea. So we act, I will just look at the center. So the derived algebra is actually coinciding with the center. And then I will get the basis when the last three vectors are spanning the center. And what I know, well, if I act by automorphisms on it, I cannot change the nature of the center. So the signature of the center will remain the same, and I always can choose the automorphism just to have this kind of diagonal matrix where diagonal entries are 0 plus or minus 1. So I can have like, space-like, or null vectors. And then I will choose, this is not C, this will be this F4 matrix, you remember the one down. So I can always choose it just to preserve this one here. And then when I do that, as you remember, the one here will also be somehow determined. So I'm just narrowing down the axial automorphisms. And then the idea is just to simplify this, but preserving this part here. Okay, and no more matrices. Let's see what geometrically happens. So here I want to preserve the center. And if the center is Riemannian, and the orthogonal complement of this is also Riemannian, well, this is easy. We can do the diagonalization. So we have diagonal matrix and everything is perfect. The same holds if we have one signature here in the center and Riemannian complement. Still basically the same reasoning. But the things gets much more interesting when we have Lorentzian complements. So here, Lorentzian center, here it's the Lorentzian complement. And this is something that I was giving a talk a couple of years ago on an unrelated topic at the Moscow State University, and I was talking about similar thing, and there was a comment that said, but that's just linear algebra. And I really got offended because I don't know for you, but linear algebra is hard. And then we actually, here, we got a pure algebraic question. So it's linear algebra. They will say you can give it to students. Well, it's not true. And I want to convince you of that. So our problem now, so this classification can be stated as, let's find equivalence classes of symmetric matrices of Lorentz signature, but the action of group is not orthogonal matrices, but orthogonal matrices with signature. So the group is O2-1. And you would say, okay, but it is basic. Surely there must be a solution. Well, it's not true. So what we just switched to geometric approach and said, okay, let's use geometry and let's restate this in the terms that we understand much better. And then we skipped to projective geometry and we said, okay, let's consider this group as a group of isometries of hyperbolic plane. And we consider the Klein projective model of hyperbolic plane. Why? Because then we can, of course, define projective conic in the standard way. And then the absolute of Klein model is nothing but this conic. So what I want to do, I want to do classification of the projective curves, but simultaneously preserving the absolute. As you can see, so I just want to act by hyperbolic isometry. So this is geometric equivalent of, let's simplify the matrix by action of matrices from O to 1. Okay, so what is here, the crucial, so our metric is going to be conic in this space. And then, okay, let's find canonical forms of projective conics under the group of hyperbolic isometries. And you will say, okay, what can we expect? Well, we know that these conics cannot be completely in or completely outside of the absolute, because our group is preserving both the interior and exterior of the conic. So it's preserving both the de Sitter and anti-de Sitter space. And then we said, okay, there must be something in the literature. Come on, hyperbolic geometry is well understood. And then we found that there are classifications, mostly by pictures. from 19th century, beginning of the 20th, the late 20th, and then there are different types, so it's not wrong. So these 9 and these 12, they're both right, just they're considering a little bit different some cases. And then we said, okay, let's see for our case, what can we do? We got by computation, but I will show you pictures because it's much nicer. So up to our knowledge, there is no explicit canonical forms available in the literature. So this is very simple, very basic question, but you cannot find just the complete classification, and you can see it in classical projective space, which every student learning about projective geometry knows. So here we have 4 classes, again by we use the previous approaches, and then they have more classes, but we are only considering these 4 because we just looking at the projective plane as a whole, are not looking at what is interior or exterior, so just as a whole. So these are 4 cases, and I definitely know how to write matrices, just I will not write them down now. Okay, and then because I was just talking about this classification where the center is non-degenerate, but let's see what did we get. So what nice geometrical properties we got. Well, as we will see later, we have unique complex structure on this group, and then we have Hermitian metric. And this is one of the questions that we will, the question about something came from the Keller geometry, and then this part was let's find some example from them. As you will see later, we did find the nearly Keller metrics, which was actually the other part of the question. Also, we have examples of both expanding and shrinking the Nil solitons. So in this case, and then we have other case when the center is degenerate of rank 2, and then again, we were thinking, okay, maybe now we can just use the algebra. Actually, yes, but we do need geometric distinguish. And then we have 3 different cases depending on this space, so spanned by two vectors that are not in the center, and the orthogonal complement of the center. So depending if it's that intersection is now, not now, or if it's actually it's inside this orthocomplement, we do have different metrics. And interestingly enough, this is not just algebraic distinction, they do have completely different geometrical properties. And then let's see, we always have parallel vector fields. We have examples of Ricci parallel, Ricci flat metrics, and the most interesting thing, we have examples of PP waves. Why PP waves? But well, this is something that we knew. If you read, there's a very nice review paper by Roger Penrose that, where he proved that every space-time can have the plane wave as its limit. So we know that if we just take Lorentzian signature metric, here we will get, in some case, PP waves. So here we just confirmed it. We do have examples of PP wave metrics. Also, in this case, we have examples of steady Nil solitons. Finally, we have, okay, not finally, one step more, we have the degenerate center of rank 1. All these metrics have 0 scalar curvature. Here we have locally symmetric, we have Ricci parallel, we have Ricci flat metrics. Again, we have some examples of PP wave. And the most interesting thing here, we prove that there is unique family of pseudo-Keller metrics, and they all are in this case. And in the end, if we have totally degenerate center, then we have only 4 families. One is distinguished here. If you remember, if I put here 1 and 1, then I will get that invariant metric. So it's here. We got it as a result of our classification. Interestingly, all these metrics are flat. They're obviously all of neutron signature, and both spaces, so the algebra and its dual, are totally isotropic for each of these 4 metrics, which is actually also quite obvious. Okay, let's go back to the arbitrary dimension, and then let's talk about pseudo-Keller metrics. So you remember that we have almost complex structure, it's linear map, which is square is minus identity. And if it's also integrable, meaning it's satisfied that its Nyquist tensor is 0 for more vectors from the algebra. So this is the relation. Then we say that this structure is almost complex structure is complex or integrable. And what we will need a little is to define abelian complex structure. This is actually a complex structure that preserves Lie bracket. Interestingly, here, this will not be true, because in order for this to be true, the center must be even dimensional. As you saw, we have odd dimensional center. We have 2 n vectors from the dual space and 1 center from Heisenberg. So this will not be true. Why is this important? Well, if we have abelian, then we can have Hermitian Riemannian metric. Oh, sorry, not Hermitian, but Keller metric that is positive definite, which is not true. So this is why I said pseudo-Keller, that's not Keller. What we prove actually that up to automorphism, the complex structure is up to a sum. So here we can have plus minus, is represented by this matrix. And this is actually result that was a long time ago, not that long, but in 2012, proven for dimension 6, so for the cotangent bundle of H3. And then we just confirmed that even if we just get higher and higher dimension, this will be still true. So we have unique complex structure, and then complex structure, so it's Hermitian if it preserves inner product. And as you remember, we did have these are Riemannian metrics. Just here, it was parameter that was larger than 0. Here, for if it's definitely 1, then this metric is Hermitian. Then we can define symplectic structure in a standard way. So these are close to forms of maximal rank, and they must be correlated to almost the complex structure. And then we say it's J invariant if it satisfies this result, this equation. And then the metric associated to any compatible pair of complex structure and symplectic structure cannot be positive definite. Well, it can, but then this complex structure must be abelian. Here it's not the case. But never mind. What we can do, we can do the classification of all symplectic forms that are compatible with our unique complex structure. And then we have some, well, it does not look like now, but trust me, this is very nice expression. So it is. It can be much more unclear. But what we know that the dimension of this space of structure of this form, we know exactly what the dimension is 3n squared plus n plus 2 divided by 2. But for n larger than 1. Why? Well, for 1, if you calculate this, you will get the spaces of dimension 3. This is not true, because if we take Heisenberg algebra H3, it has a little bit different decomposition of the space of 3 forms in this basis. So we have 2 additional elements. So here it's 5, but for every dimension larger than, so for every n larger than 1, the previous formula will hold. And then, of course, we do have pseudo-Keller metrics. And as I previously mentioned for Heisenberg group 3, we had unique family of pseudo-Keller metrics. This is also true even in higher dimensions. So we have unique family, and they're they are not flat, but they're pretty flat, which is also something that is nice and of importance to people doing geometry. And then finally, the question that was asked by the group of people doing Keller geometry, let's talk a little bit about connections. So there is a Catan's, let's say, statement that given a manifold embedded in some affine space, we can attribute to it some affine connection that reflects in the simplest possible way the relations of this manifold and the ambient space. We can talk about affine connection, but we can just skip, just change it and talk about projective or conformal or whatever. So we want to know what manifold and the ambient space are, how they are related. And then geometric interpretation of this is we have Riemannian manifold, we have Levi-Civita connection on it, and we have any linear connection. And then what we can define this 2-1 tensor as the difference between these connections. And then we say that this linear connection is torsion-free if and only if this tensor A is symmetric, or that these two connections have same geodesics in case of A being skew symmetric. And using this, so I just contract this to get 3-0 tensor, and then I can define the so-called torsion tensor. Why is this important? Well, because there's a classification of these torsion tensors done by Tricheri and Van Hecke in the beginning of the 80s. And they said, okay, a space of all possible torsion tensors can be decomposed into three subspaces. So the first one, those are connections with vectorial torsion. The second one has no special name, but as you can see, you can have the cyclic sum of this that will be 0, and then again, when you apply it to the vectors, basic vectors of the space, you can again get 0. And the third one, those are connections with skew symmetric tensors, so given by the following condition. So we know what these spaces look like. And what we know that if we have Hermitian metric, the torsion will belong to the full class. So we'll have part in all three parts. But what if we lose integrability condition? What if we only take almost complex structure? And interestingly enough, so if we take this pseudo-Kähler matrix, the torsion will belong to completely this third part. And this actually is nearly Kähler manifold. And this was the only positive answer that we got to all the questions that we were asked a couple of years ago. Okay, and finally, I will tell something about sub-Riemannian structures. I don't know how well acquainted you are with sub-Riemannian geometry. It's usually called Riemannian geometry with constraints. And when people talk about it, they always start with some examples from physics. So they talk about satellites or some mechanical examples. Or if they want to talk to broader audience, they talk about parallel parking. I don't know about you, but I hate parallel parking. So we use something that's for me much more interesting. And this is a wonderful example given by Richard Montgomery in his book, Tour of Sub-Riemannian Geometry, when he calls sub-Riemannian geometry, geometry of a falling cat. So you take a cat, legs, and then you just drop it without spinning. So it's falling. You want it to land on its feet. So what happens? Well, the cat is just making some, in the shape space, there's some curve, but that curve corresponds to the real physical shape of the cat falling. And then it's just, when you woke up today, did you think what will be holonomy group of a falling cat? Of course not. But holonomy group of falling cat is just rotation through the body axis for 180 degrees. But what the cat, so this is very natural thing. Cat wants to straighten, but how? Well, the most efficient way. So along the shortest paths. And then we actually have something that's called the isoholonomic problem. And now you see why this comes from the theory of optimal control. You want to optimal part. So this is not real cat. This is not even a chat GPT. It's just the drawing. So no cat was hurt. Okay, in the Riemannian geometry, we always talk about some manifold, and then we have metric on that manifold. This is not enough for sub-Riemannian geometry. We need three elements. We need, okay, in our talk today, we will need Lie group, we will need distribution, and then we will need metric. So we'll need a real finite dimensional connected Lie group. And then we will need a distribution of constant rank. It can be defined if the rank is equal to n, then you get just tangent space. But I will exclude this because this is non-holonomic geometry, not sub-Riemannian geometry in the purest sense. So let's say it's always less than n. And then I have a Riemannian metric on this that will be in some way just restricted to this distribution and will smoothly depend on the point. When I say Riemannian, actually it's not just if you take a Riemannian and then just put it in the distribution, you will need to find an inverse and something, but if you're not doing anything in sub-Riemannian geometry, don't bother. So if we know Riemannian, we can reconstruct sub-Riemannian metric. This is important for now. And then we have the so-called horizontal or admissible curves, or sometimes called D curves. So we want to have a curve on a manifold or on a Lie group, but tangent vector, we just want it to be in the distribution. So not the whole tangent space, but just to always just land into the distribution. And if I have that, then I can define Carnot-Theodori metric, how well I have all the paths connecting 2 points, and then I just get infimum of the length. If there is no path, then you say, okay, it's just infinity. And the curve that is realizing this distance will actually be called minimizing geodesic. And now, because I already said maybe there is no path, well, we can just skip that if we have additional condition on this distribution. So not just any distribution, but the bracket generating or completely non-holonomic distribution, depending which literature are you reading. So I just want to take vectors that are spanning distribution. And when I apply Lie brackets on those vectors enough time, I can generate the whole tangent space. This is the idea. And then if I have this bracket generating condition, then our metric is complete. And every 2 points can be joined by a minimizing geodesic. So this is very strong condition. And first, the result here. So we can say that all sub-Riemannian structure as a metric to exactly one of the structures. So I definitely know what distribution. This is the minimal distribution. So all the vectors from our initial group except the center. So just because I know that central elements I can get by just applying linear bracket on these vectors. And then this is the Riemannian corresponding Riemannian metric that we get from our classification. It's said that sub-Riemannian structure is tamed by a Riemannian structure if it's actually just projection on the distribution. Again, not quite, but let's say for this talk, it's enough. Again, we have take orthonormal frame. These vector fields are the ones that I showed in the beginning of this talk. And then again, so I can have the basis and I know completely well this space. Why we are looking at this? Because we want to look at the geodesic lines. And every geodesic of some arbitrary left invariant on Lie groups can be seen as a motion of generalized rigid body with configuration space G. And this is something that is quite used. And this is something that has a lot of connection with Hamiltonian mechanics and Hamiltonian geometry. But let me just show you what is difference between Riemannian and sub-Riemannian case. So in Riemannian case, every geodesic is defined by a point that it passes through, and the initial geodesic vector, which is actually tangent vector to it. But in sub-Riemannian case, we don't have tangent vector, but we have initial momentum. So this is the first difference. The second one is that all pseudo-Riemannian geodesic on two-step nilpotent Lie groups are geodesically complete. In a sub-Riemannian case, when you have two-step nilpotent Lie group, and then you just switch to sub-Riemannian geometry, it's called two-step Carnot groups. So for the ones that would like to learn more about this. And the sub-Riemannian normal geodesics, so here one word is missing, are exactly the projections of the Riemannian ones in this case. Why I say normal? Because I forgot to write this down, but the interesting thing about sub-Riemannian space is that you have geodesics that do not depend on metric. They just depend on the distribution. And those are not solutions of the Hamiltonian equation. Not every sub-Riemannian structure have abnormal geodesics. So this was one of the questions, can we have it here? Of course not, because this is a very special group and the distribution is very special. So we have only normal geodesics that are solutions of the Hamiltonian equation, but there are some examples. And I'm finishing because, no, here just the pictures. One is just, so to look here, the geodesic, so to pull one is a Riemannian geodesic. Okay, this is 6-dimensional space, I have to do some projection. But see, when I just say, okay, we cannot travel in every direction. So here, this is the sub-Riemannian one. This is a projection on the Heisenberg group, but if I project it on the distribution here, again, so it's quite different. So thank you, I'm done.
We're very excited about the talk. But maybe we can have one short question, or if not, then
Where is the gap in the picture?
Yeah.
In the geodesic picture, look at gap.
Unfortunately, it's not falling like that.
Ivan, did you want to say?
I wanted to ask a question. So
Okay,
two-step
first
neo, short, yeah. Two-step nilpotently algebras are coming from graphs. So do we see the graph like in this geometric picture somehow? Like
I have no idea. I was not thinking about that at any point. So actually, the most I'm interested is this sub-Riemannian problem, but not this one. So you can define some different structures and then look at them. And now, so I'm not thinking about graphs. I'm not even thinking about Néel manifolds at this point.
Okay.
It's always that, yeah. And I think next class will be like